molecule. If you draw 10 things with chlorine, once at the top here, once at the side, once at the top, once right, down, left, right, and here, you're going to see some duplication, right? So think first looking at this molecule, is there symmetry, or maybe categorize each carbon as primary or secondary, or use some of the tools we've developed in the last 30, 40 minutes that we've been together today and from our last class. I'm hoping that you came up with two unique products. We have primary and tertiary carbons here. And the question is this primary and this primary the same? If we put one chlorine off the right, is that the same as if we put one chlorine off the left? Yes, those two molecules would be the same. Well, let's use this as our reference again. If chlorine's off to the right, and we put a chlorine down here and compare those two molecules, are they different or are they the same? Those two are also the same. All three of these methyl groups will be identical, and if you're not convinced, then you should draw out the products from them. The central carbon is definitely different. We even characterized it as tertiary. And if we put chlorine in the middle here, that'll be much different than chlorine coming off the side. Let me draw those particular products, and hopefully you have something similar. Again, in these activities, even if we were live and direct right in front of one another, you might actually draw the chlorine off the bottom methyl group. Or you might draw the chlorine off the left methyl group. Or you might draw the chlorine going up here instead of to the right. Please recognize all those different things I'm describing are all right. They're all identical. So, if you don't like this right carbon for some reason, fine, use the left one. You get the same exact product, and if you were to name this thing, you'll get the same name. We can also see that this particular product, the chlorine has been inserted at a primary carbon. Let's draw the other one. The other possible product is this T-butyl chloral compound. And we can see that chlorine is dangling off the middle. And if we look at this overall molecule, it's 2-methylpropane, but in one case, the chlorine's at position 1, and in the other case, the chlorine's at position 2. So if we were actually to name these compounds, the names would be different. If you were to draw any other variations on this, it would have the same name as this. So, these are the only two possible products. If this was difficult for you to grasp, let's talk about it at our break sometime around 10 or 10:15 today. The ratio of hydrogens here is 9:1. There's 9 primary hydrogens for every 1 tertiary hydrogens. The product distribution is 66% to 34%. This is a yield. It's an experimental number. Don't need to memorize it. But still, chlorine, we can say from this result that chlorine has a preference for the tertiary position versus the primary position. Chlorine still has a preference for the tertiary position versus the primary position. Clearly, it has an energetic preference for the tertiary position. If it didn't have a preference, then this should be 90% to 10%. If statistics were at work and there was no energy difference between primary and tertiary, then this should be 90%, 10%. So chlorine here still has an energetic preference for the tertiary position. It somehow prefers to go here. If it didn't have a preference, this should be 9:1. So this is still a reflection of the fact that tertiary radicals are more stable than secondary or primary radicals, and we'll see that work its way out as we compare and contrast this today to a different halogenation reaction. Okay, so get it through your head here what this means. Chlorine has a clear energetic preference for tertiary positions or secondary positions. I didn't say it was the major product. I'm just saying it clearly has an energetic preference, which it does. Let's recall propane. We'll go back to easier molecule. We're going to take propane, and we're going to treat it 2 different ways. Once we're going to treat it with chlorine and heat, and in the second reaction, we're going to treat it with bromine and heat. We didn't explore bromine yesterday, but the mechanism of radical bromination is 100% identical to the mechanism of radical chlorination. 100% identical. The only difference is the letter is different, Br. When we do this particular reaction, we saw in our last class that we got two products, and that they were a primary and a secondary product, and they were recovered in about 50% yield for each of them. Again, chlorine clearly is preferring to go to the secondary position because there's much less secondary hydrogens. This becomes amplified with bromine. Bromine's special in this sense. We still make the same two products. The difference being we have bromine now. Okay? Well, that's just because we switched which halogen we're using here. Recall, fluorine is explosive. Iodine is very slow and doesn't really work. But chlorine and bromine behave identically. We have a primary product and a secondary product. Bromine differs from chlorine in one peculiar way. Bromine differs from chlorine in one peculiar way. Bromine is much more sensitive to the stability of the radical that this bond was formed at, or this bond was formed at. Bromine is so sensitive that the product distribution is 2% of the primary and 98% of the tertiary. In this case it's secondary, I misspoke. This particular reaction, when we use bromine instead of chlorine, we get a different product distribution, a different yield. We get only 2% of this primary alkyl halide, and we get 98% of the secondary alkyl halide, and that's because bromine is very selective. You can make that note here if you want, but we're going to reiterate it momentarily, and I'll write it out for you. But bromine is very, very sensitive to radical stability, so much so that it barely makes any of the secondary product or the primary product if it has a choice to make a secondary product. Let's revisit and hammer home this idea with another simple example. It'll also give us more practice for bromination. Let's just recall something we did moments ago. We're going to take isobutane again. And we'll do the same kind of treatment to it. Chlorine, heat, bromine, heat, or we could use UV light. The yields for this on the previous page, we just actually did this, were 66% of the primary product and 34% of the tertiary product. And we'll draw them actually out for bromine so that you know exactly what we're looking at together here, or how it changes. This would be the primary product that we would get if we put bromine dangling off this methyl group, or this one, all the same. The other product we could get here is the tertiary one. Where bromine's been inserted at this tertiary position. Okay, you should be able to practice this whole propagation steps to make this and this with a mechanism. We're not going to do that in class. It's something you can do on your own. Bromine is so sensitive to primary versus tertiary radicals. Actually, nothing is formed of the primary, and 100% of the product isolated in this reaction when we use bromine goes towards the tertiary position. There's something very simple we'll remember about this, and then we'll explore the energetics of this carefully. What we're going to say here is that chlorine is more reactive than bromine. So chlorine is more reactive than bromine. Therefore, it is less selective. In these radical halogenation reactions, chlorine turns out to be more reactive than bromine, and therefore it's less selective, or we could think of it as being more random or going everywhere. Conversely, bromine has opposite traits. Bromine is obviously less reactive when we compare it to chlorine. And if it's less reactive, therefore it is more selective. So these are a general idea or concept I want you to remember. It applies to all chemical reactivity, but we're going to apply it very simply to chlorination versus bromination. Chlorine is more reactive than bromine, and therefore it's less selective. Bromine is less reactive, and therefore it's more selective. Bromine, if it has a choice, it's going to go after that tertiary position almost every time. If it has a choice between primary and tertiary, it's going to go almost exclusively to the tertiary position. Chlorine, if it has a choice, it's going to go everywhere, all positions on a molecule. But bromine, if it can find a tertiary position, that's where it goes. And so this idea of high reactivity being associated with low selectivity, or low reactivity being associated with high selectivity, is kind of a general principle in nature. Highly reactive things are very non-discriminatory. They go everywhere. And less reactive things will be more discriminatory, trying to find the most energetic place, the most energetically favorable place to go.